100 years ago, Albert Einstein came up with a new model to describe the behavior of the universe. At the time, people thought it was a beautiful model and was relatively simple. Like in the Animal House scene, Einstein came into the parade, took the baton from Newton, and has led the scientific revolution ever since, down the alleyway. And they're still in the alleyway. For the last 20 years, it appears we've reached a dead end by pursuing theories based on Einstein's theories of relativity. It's become incredibly complex and created problematic issues in other areas of science. Dozens of observations over the last 100 years have conflicted with Einstein's theory of relativity. And at every one of those points over the last 100 years, we've rationalized the observation to the consensus model. And we've ended up with piles and piles of theory on top of theory that could be very, very well off in the weeds right now. Everything done since the early 1900s has assumed that Einstein's theories for relativity are correct.
Anytime you hear people going around like they are today, congratulating themselves how they have these theories that predict all these things. And aren't we so smart? Well, let me tell you how smart we are. When you take the quantum theory as it exists today and try to join it with a analysis of the universe based on Einstein's general relativity, you find that they are off by 10 with 120 zeros. There has never been a larger disconnect in the history of science than we have today. And what do we have? We have people writing books like The End of Science. We know it all. Down at the bottom, it's rotten. And we keep putting Band-Aids over it.
After all is done, after all is said, after you are gone, I go and bang my head against the wall. I swear it doesn't hurt at all. I swear I like the pain.
I'm still asking myself the same question that I asked myself 10 years ago. That's what is going on in my community. We build particle detectors, try to find dark matter. We build larger colliders in the hope to produce no particles. We shoot satellites into orbits and try to look back into the early universe. And we do that because we hope there's something new to find there. And we think so because we have some idea from the theories that we've been working on that this would be something good to probe. But there are actually a lot of questions that have been around for decades. Like, for example, what is dark energy? What is dark matter? Why are the masses of the standard model particles what they are? And what's up with the foundations of quantum mechanics? If we are working with the wrong theories, we're making the wrong extrapolations, we have the wrong expectations, we make the wrong experiments, then we don't get any new data, we have no guidance to develop these theories. So it's a chicken and egg problem. And I think we have to break this cycle. And I think we've reached this point where we have to very carefully rethink if the criteria that we're using to select our theories are promising at all.
All the shit you told me is stuck inside my head. All the shit we did is fucking with my brain. I won't complain. I know you like the pain.
When you observe an anomaly that's inconsistent with a theory, at each point you do that, you've got two choices. One is to invent or discover something that makes it work mathematically with a theory, and the other option is to go back and find out what was wrong with the core model that made the observation inconsistent. And at every turn, our scientists have taken the easy route, which is to invent something new to make the observation rationalize with the core model, instead of going back to the beginning and finding out what was wrong, what mistake was made in the core model. In the mid-1900s, telescope technology had reached a point where we could actually observe stars moving around the Andromeda galaxy. And the observation that we made was that stars are moving too quickly to be explained within Einstein's theory of relativity. Scientists took the observation, turned it over to mathematicians. Mathematicians calculated you needed 5 times the matter. Boom, they invented dark matter. They changed the physical construct of the universe to defend Einstein's gravitational theory. Dark matter is invisible matter that we cannot see and so far, after billions of dollars in research, cannot even detect. For 2,000 years before Einstein came in, there was the assumption that space was filled with an ether. And the ether had physical properties that would interact with other objects. There was always the use of an ether within the model. And the first principle that Einstein changed was eliminating physical properties in empty space and literally making ether a dirty word in the physics community. Now, for the last 100 years, scientists have been trying to sneak something in that sounds a lot like ether dozens of times to explain anomalies that they couldn't explain without an ether. And at each point, they never call it ether. It's dark energy, or it's vacuum energy, or string theorists have a different idea, but it's something that looks and smells and sounds a lot like ether.
Let me start by telling you a story. Imagine that there were a planet that was immersed in a deep ocean. What would their conception of the physical world and of physics be like? Well, at first, they would regard their surroundings, the water, as just the way things are. They wouldn't have a concept that there was a world without water. That's the way it always is. They'd think of that as space. That's what space is. But eventually, as they got more sophisticated, they'd start to think of water, space for them, as a material. The big idea that I want to convey, we're like those fish. We're ethereal beings. We're children of the ether. Really? Didn't you read that ether is totally discredited? That it was something that went out with the theory of relativity in 1905? Einstein really didn't like it because the medium would have to have very strange properties, namely the properties that he wanted in special relativity. And he thought that was absurd. No material could have that property, so the heck with it. This is a picture of empty space. What we perceive as empty space is actually a medium that's full of spontaneous activity. The brighter colors indicate a higher density of energy, and the lesser colors are lesser energy. And you can see that there's weather in space. Space has many properties that you would think of as associated with the material.
I think scientific revolutions are precisely the moment in which physicists or scientists in general can no longer avoid to ask questions about first principles. Maybe there is a completely alternative theory that just gets rid of the hypothesis of dark matter and even maybe dark energy. So we are here at the tipping point. Why does matter deform space, and so on and so on? All these things are left unexplained. So gravitation is still unexplained. If a new kind of particles is found, then that will challenge the whole of quantum field theory. If a new type of theory of gravitation is found, then it will be a challenge to general relativity. So clearly we are exactly at the point where we must expect a huge scientific revolution, a complete renewal of the paradigm, which is quite exciting.
A paradigm shift is a change in one of the first principles, the core assumptions to a theory, what all the other theories are built off of. Science has a way of evolving two ways. One is evolution, where you add theory on top of theory on top of theory to come up with the latest consensus model. The other is revolution, which is having to go back to the core theory, change it, which affects all the other theories that have been added on over time. It's similar to a Jenga tower. where you have foundational theories at the bottom of it. If one of the core theories on the foundation is wrong, and you remove that theory, there is the possibility of all of the theories tumbling down. It's incredibly disruptive to the existing scientific establishment, is the downside. The upside is it allows enormous room for creativity and improvement going forward. Einstein's theory of relativity is in the foundation of today's scientific Jenga tower, and the removal of ether is the key component of Einstein's theory of relativity. So all big dollar research is limited to Einstein's theory of relativity. Anytime an observation is made that might require someone suggesting that Einstein might have made a mistake, the solution is to then invent something that would make it coexist with Einstein. What we're operating under today is the Church of Einstein. It is very similar to what happened with the Catholic Church, with the exception of we're not burning people at stakes. In the 1600s, the Church was responsible for all scientific research back then. And the Church was heavily invested in predictions made by the Bible. And one of the first principles back in 1650 was that the Earth was the center of the universe. When Galileo made observations that showed that the Earth wasn't, the Church went into defense mode, and they spent 20 years doing mathematical gymnastics to try to take Galileo's observations and work them into a model that would leave the Earth at the center of the universe. You had planets doing retrograde orbits. You had things that made no sense whatsoever, but the scientists that were doing the work couldn't comprehend the idea that that first principle, the Earth is the center of the universe, was wrong.
The Church was like the gold standard of what truth is. Galileo was challenged by the Church because he was claiming to say the truth. And according to the Church, it was not possible because the truth was contained in the Bible. Okay, Galileo, we accept your theories, but don't claim that they are the truth about the world. Just say that they are a way to say phenomena. Just an empirical tool to predict phenomena and be right in saying that next year there will be an eclipse and so on. And that we accept, no problem.
We can say that Galileo was the founder of the modern sciences, but we don't have any, in Italy, any statue of Galileo. We have some statue of Leonardo, and for the other, Michelangelo in Florence. In the case of Galileo, was the first time that we have a contradiction between the perception of our science and the reality of the facts.
The most important thing of Galileo is his peculiar use of the telescope, because he just used the telescope to observe the sky in a time when all people believe that everything has already been discovered.
Many people say that Galileo was killed by the church. That is not true. There are cases that that is true, but not the case of Galileo.
He was not condemned to death, but to house arrests, as we would say today, for the rest of his life.
What is the reason that the Pope supported an Academy of Sciences for many years? Because they believe in the truth that comes from science.
Now we don't have the gold standard, but from time to time a paradigm can play the role of a gold standard. But then the gold standard of truth shifts from one paradigm to another. Well, presently there is no church that can decide anything about the contents of science, yet there is a sort of inertia of science itself that can play this role of saying, no, don't change, we don't want to see this change. Galileo was a little bit outside. He was outside the Aristotelian mainstream, and he was really criticized. You know, people didn't even want to see through his lenses because they said they are distortive. They distort reality, so we don't even want to look through them. When you write a project for a grant, you have to know what you will discover. And this project has to be credible to other scientists, and other scientists obviously are very much trapped into their paradigm.
We're still using the same techniques, we're still working with the same theories as we did in the 1970s. The interesting question is who makes the decisions about the funding, and superficially people say, well, it's the funding agencies or it's the university who get to hire people, but that puts the blame on the wrong party, because in the end it's the community itself who makes the decisions. That's because what do the funding agencies do if they get a proposal? Well, they send it to reviewers. And who are the reviewers? That's people from the same community. What the people in these committees would be doing is they would be looking at easy measures for scientific success. And presently the most popular of these measures are the number of publications and the number of citations, and maybe also whether the person has published in high-impact journals. So these are the typical measures that are presently being used. But what do they measure? They measure primarily popularity. They indicate whether somebody's research is well received by a lot of people in the same community. And that's why once a research area grows beyond a certain critical mass, you have sufficiently many people who tell each other that what they're doing is the good thing to do. They review each other's papers and say that that's great and that's what we should continue to do. But of course, experience moves us forward until it doesn't. I think that very plausibly the main reason why we haven't made progress is that we're not doing the right thing. We're letting ourselves be guided by the wrong principles. It worries me because I have to question how well science itself is working. The problems that I was speaking about in my own community, that people work on certain topics just because the money is there, because it's something that is popular, that their colleagues appreciate, and my extrapolation from my own field would tell me that I should be very, very skeptic about whatever comes out of the scientific community. And that's not good. Clearly, that's not good.
What troubles me the most, quite frankly, is that I have never seen any course where we teach our undergraduates about these problems with the current theory. People teach that material as if it was true, when it can't possibly be true. So that has to change. Science is about being honest.
There is almost nothing in our consensus model, either studying the very, very small or the very, very large, that would make us believe that we have a logical understanding model to work with today. There's something wrong in the foundation. And the only way to fix that is to go back and find out what's wrong, correct it, and then reevaluate all of the observations through that lens. In the lens before general relativity, there was an ether. In a model based on ether, matter attracts energy. Matter needs energy in order to create its electromagnetic field and all of the things that it does on a normal basis. So ether is a fluid form of energy moving through empty space. The nuclei of an atom will suck in energy, which is the ether, like a jet engine will suck in oxygen. That energy gets sucked into an object. All matter is attracting energy from ether, from this region of space. There's no forces inside of an atom. The energy is coming from the ether. We see gravity around large objects. What are large objects? They are nothing more or nothing less than a boatload of atoms combined. That's all they are. When you have a large body like a planet, what's happening is the energy as it converges on the Earth provides a drag. It interacts with the fields in your body, and the result of that is what we observe as gravity. There's a constant flow of energy that's going toward the Earth, and we're affected by the current headed toward the Earth. It is a physical energy transaction stimulated by the need for small objects to be powered. That's gravity. With a model that has ether included in it, whatever we observe happening at the large level would be a function of the cumulative effect of whatever's happening at the small level, because all large things are just large groups of small things. You can then tie the behavior of an atom to the behavior of a planet to the behavior of a solar system to the behavior of a galaxy mathematically, continuously. You can create a model that is unified from the very, very smallest items to the very, very largest systems in a model that has ether. If you look at nature, nature has a way of repeating herself when something is successful. The purpose of a hurricane is nature's way of reestablishing a balance. It spins all of the imbalanced atmosphere around it, brings it into the middle, and in the middle, a balancing mechanism takes place, which is the eye of the hurricane is a low pressure zone. Well, the galaxy is exactly the same thing. The construct of a galaxy and the movement of a galaxy is simply nature's way of correcting an imbalance, which creates the formation of a galaxy around what we call a black hole today. And you end up with currents of energy going into the galaxy. The direction and speed of those currents are affected by the rebalancing mechanism, which is the energy coming out of a black hole. If you look at a picture of a black hole, you'll see these enormous energy plumes come out of it, which is completely contrary to the idea that it's so dense that light is trapped in it. That is energy being converted from mass back into a clear state, shot back into the universe, and reestablishing a balance in that region of space. The interaction with the return of it, with the energy being drawn in, creates the swirl, just like it does in an atmospheric event in a hurricane. And all the solar systems in the galaxy are being driven by a current of energy that ultimately will end up in that black hole and redistributed in space. The reason they added dark matter in there is because the Andromeda galaxy would spin off into space based on Einstein's theory of gravity. Let's change everything about what we know about the universe so that we don't have to go back and revisit gravity. And to me, it's like, yeah, come on. The only thing wrong with our model today is our definition of energy. So if you redefine the properties of ether properly, using our observations over the last 100 years, you redefine it, it's not pushing things apart. That's a Band-Aid. Energy is actually traveling toward large objects rather than pushing them apart. Early 1930s, Edwin Hubble made this observation and said, there's a redshift, and something is affecting the light as it moves through space. Einstein's the one that took it and said, we believe that the universe is expanding because the distant objects appear to have a longer wavelength in the light that we're observing. Think of the Doppler effect with a siren in an ambulance. If the ambulance is moving away from you, the wavelength will spread out. Well, Einstein jumped all over it because Einstein, to make relativity work, the universe either had to be growing or shrinking, or relativity was wrong. He saw that and he goes, fabulous, it's growing, and we got the expanding universe. The primary reason we have a Big Bang in our theory right now is because we believe the universe is expanding. If you take that out, and you take what I would assume, and a lot of other scientists do, that it's a static universe, there's no reason for a Big Bang. And it turned into the catch-all for everything. Where did matter come from? Big Bang. Where did gravity come from? Big Bang. The Big Bang's the catch-all for all illogical theories that we have out there. What Einstein got rid of, which really helped him with his definition of light, was any resistance in space. In anything in nature that we can observe as a wave has a medium, whether it's in water or the atmosphere or the ether. There's a medium that it travels through that it disturbs, and it's the same thing with light. Another way to get a redshift, with a model that has ether included in it, light is affected by space travel. It's traveling through an ether, there's a drag, there's a travel effect on light. So as that light is traveling by millions of galaxies, there are different levels of resistance for the light traveling through the medium. We have no idea what's happened to that particle as it went through space. It could have gone through large clouds of hydrogen. It could have gone close to galaxies and been bent. Another way to get a redshift is to bend the light. There's no reason for a Big Bang. The other question the Big Bang is used for is what started everything? And the Big Bang doesn't answer that question any more than God answers that question. Scientists have observed a cosmic microwave background, and they've assumed that it was echoes of a Big Bang. You know, there are 30 other things that it could be looked at through different theoretical lenses. It could be temperature fluctuations, different concentrations of ether in different regions of space. What we're doing is we're expecting to find something, and we find something, we assume that it confirms. You can manipulate an observation into what you want it to be based on theory. A real interesting example of sort of institutional bias was done to a well-respected cosmologist, Holden Arp, who had his telescope privileges removed because he was making redshift observations and coming up with very different conclusions than an expanding universe. And that is a real threat to the scientific community. If the universe isn't expanding, or if any of these core theories are disproven, then the whole thing could fall apart.
The important thing, I think, is to see the observations, to communicate the evidence, so that everyone has to make up their own mind on this.
So one of the other small failures, things that we can actually see that conflict with Einstein's theory of gravity, is what they call the flyby effect. Whenever our scientists slingshot a satellite around an object, the departure speed is always different than what general relativity would predict. And that's something that can be explained within the fluid ether model. The currents that travel toward an object aren't the same. The north and south poles will have a different direction to current. It's like if you drop a cork into a river. There are eddies, there are different things going on at different points in a river that will vary the speed and direction of the object. And there's currents headed into large objects that have other variables involved in how the current flows, including the spinning of the object. And that will affect gravitational behavior. You could have SpaceX launching projectiles to slingshot around the moon or slingshot around Mars and measure the speed going into the slingshot, the speed coming out of it at different angles, and come up with data points that will allow you then to model the way that the energy current is flowing into that object. In Einstein's model, where a large object is bending space-time, that shouldn't happen. The orbits should be consistent regardless of direction. We're seeing anomalies that conflict with Einstein's theory of relativity every day. We have dozens of examples of it failing as a theory, and in not one instance has the scientific community ever really questioned going back and redoing the theory. To convince people that the theory of ether is right is to create a theory that answers all of the observations that we've made over the last 100 years and before better than the existing theory. I believe that if you introduce the ether theory as a credible theory, there will be dozens of ways to prove the existence of ether. Michelson and Morley in 1887 did an experiment in Columbus, Ohio, to go test Newton's theory of a static ether. And they did that by creating an interferometer. And the theory would have made it if the Earth is traveling through a static ether, light would bend based on the orientation of where that interferometer was on the Earth's surface. The interferometer took light, ran through a prism, and separated it into two different flows, running at perpendicular angles. And the theory was that if there was a static ether was moving through, those beams of light would come back at different times. And they didn't come back at different times. Therefore, there was no static ether the Earth was traveling through. And the conclusion there, which I think is probably the biggest mistake we've made in misinterpreting scientific observations, is that there was no ether. Einstein took that, and that was the primary data point he used in his theory of relativity in eliminating an ether. Our ability technologically to create an interferometer today is significantly greater than it was in the late 1800s. And our ability to measure changes in the observations, the sensitivity of the equipment is significantly better. If we ran that same experiment today, changing the orientation of the light beams would be an interesting thing to do. Because if there is a medium that is traveling through and the medium has direction, then it should affect the movement of light. You're going to see a deceleration of the speed of light up, and you're going to see acceleration of the speed of light down. When it is going against the medium, it's going to go slower than it will when it comes down from the medium. Slowing it down in the vertical direction and speeding it up in the reverse direction. If the core theory is wrong and you have 100 years of massive technological advancement and massive scientific observations, and you're going in the wrong direction, you're going to be way offline. And in order for advancement in several areas, we depend upon our sciences having breakthroughs. The ultimate responsibility for how we spend our education and research resources comes down to people. We're the ones that are funding all of this. We fund it through our taxes, we fund it through our educational institutions and so forth. I don't know anybody, at least in my peer group, that is satisfied with the directions that are being given to us by the current status quo model. I think the only way to change this, the only way to break the inertia of the scientific establishment is to have people begin to ask questions and say, okay, that's a lot better than that. It makes a lot more sense to me than that. You tell me why yours is better than that. They need to defend what they have. I think the most important resource we have going forward is the next generation of scientists. And we are doing them a massive disservice if we don't allow them to question all of the things that we present as theories. We need to be able to have an open dialogue about that without risk of having your career ended or getting an F on a test. I mean, for a scientist to advance today, he's got to regurgitate everything his professor taught him, who is regurgitating everything professors 3 generations ago taught their guys. And it's just this cycle that needs to be broken. And the only way to break it is to embrace people questioning status quo. And so the question then becomes, if we continue on the same path we're on, continuing doing the same research projects and the same educational processes and so forth, are we going to find out what's wrong? You know, back in 1650, if we continued along the path there and we didn't question whether the Earth was the center of the universe, would we have ever discovered so much what we know now? No. If you eliminate the illogical assumptions that they've made, just say that's not acceptable. You don't get to increase the matter in the universe by 5x because your gravitational theory just fell apart. You know, you don't get to redefine the universe. That's unacceptable. If you hold them to that standard, which we need to hold them to, they can't hold themselves to it. They need the status quo to continue to maintain their lifestyle. It's our responsibility to do that. I think one of the, it's almost childish things about physics today is the inability to use the word ether. I mean, they've tried to plug things in, physical properties of empty space, which is what ether is, for 50 years, but they can't use the word. So the guy who first called bullshit on it was Einstein, on his own theory.
To deny the ether is ultimately to assume that empty space has no physical qualities whatsoever. According to the general theory of relativity, space is endowed with physical qualities. Therefore, there exists an ether. Space without ether is unthinkable.
Yet the establishment ignored him, which is phenomenal. It's a good example of the inertia of the physics establishment, but they ignored Einstein. If you can't question the status quo, and the problem is in the status quo, you're doomed. What is the old saying that the definition of insanity is doing the same thing over and over again and expecting a different result? Well, that's what we're doing right now. When an anomaly shows up, we can't sweep it under the rug. It's got to be free game to go back and question first principles. Once you're allowed to have that conversation, the outcome may be very different than I think, but we need those young minds to begin working on creative solutions. And, you know, I think it's been really hard to do that within the current institutional structure of physics, but I'm hopeful.
My own take is we're on the verge of another scientific revolution that's just as big as the one that happened 120 years ago. And nobody's seeing it, just like nobody was seeing it back then.
The possibilities are completely open to other options. Sometimes a theory that looks completely outdated in physics can find a new youth. You know, what looks like a cemetery of ideas, in fact, is a repository of ideas that can be used again and again. For instance, the ether.
We can't understand the behavior of the things we do see if we don't ascribe space itself those properties. So space is not a void.
So I've been thinking for a lot of time how we could go about and try to solve these problems. And it's hard, but I think it's really necessary.
So you see, we are still on the border between two paradigms, which is probably the most exciting moment in the history of science.
We've paid a hell of a price for sweeping stuff under the rug in the 20th century. We're still doing it. And everybody knows that something's wrong.